a really big topic in calculus, whether we're doing derivatives, and it's going to come back in antiderivatives, is straight line motion. And what we're going to be talking about is position, velocity, and acceleration. So position is like the original function. If you picture you're in a car, you're driving to San Diego, let's just say your destination is San Diego. I think we've all been there. And so let's say you're going to San Diego. Your position's where you're at. How many miles have you traveled? And let's just say your starting point was Holtville. If you're in the mountains, maybe you just started in the mountains, you're like 50 miles into the trip. That's position. Velocity is very similar to speed. How fast are you going? Now, I think in the typical physics class without calc base, you have to learn how to do average velocity because average slope. But for us, we're able to find the instantaneous velocity. We're able to find that instantaneous rate of change. So if you're driving to San Diego, if you hit cruise control at 75 miles an hour, 70 miles per hour, you're going to stay that way the whole time. But that's your rate of change. You're changing 70 miles per hour or 75 miles per hour. And that's going to vary throughout the trip. So we're able to find, using calculus, the exact speed at that very moment. So that being said, velocity is the derivative of position. And we'll call it S of t. Usually S of t, position's usually called S of t or X of t, because usually they think of this as like the x-axis. So derivative of that function. And we're actually taking in respect to time now. Same thing, just using t for time makes a little bit more sense. So velocity is the first derivative of position. It's the rate of change. Now, it's not exactly speed. How does speed differ from velocity? Speed doesn't tell you direction. Speed is equivalent to the absolute value of velocity. It's kind of strange that S of t is used for position. You'd think it would be used for speed, but a lot of times used for position. S of t and X of t, they kind of interchange those. Maybe we should just say X of t so you're not confused with speed. Oops. So speed's the absolute value of velocity. What does that mean? Well, let's just say you turn around and start going towards Yuma. You ever had that trip where your mom's like, okay, guys, if you keep fighting, we're going to turn around and go home? Well, let's just say, my kids are fighting, whatever. And so we canceled the San Diego trip. So we turn around, we're heading back to Holtville, we're heading towards Yuma. If you pass Holtville and you start going to Yuma, you're in a negative position, right? Your goal was to go to San Diego, but now you've gone too far, you're now in the negatives. That's what negative position would be. But velocity tells us a direction. If it's positive, we're going forward. We're moving towards our destination like you see here. We're going towards San Diego. If our velocity is positive, we're moving forward. So it's kind of nice that it tells us that. So if v of t is positive, then x of t is increasing. If v of t is negative, then x of t is decreasing. So if we have a negative velocity, then we're traveling back home. We're heading the wrong direction. We're heading this way to the left. That would be a negative velocity. To the right would be a positive velocity. So velocity tells us direction. Speed, it doesn't matter which direction we're going. If you're going 70 miles per hour, you're going 70 miles per hour. You're not going to say a negative speed. It's only positive. That's why it's the absolute value. Last, acceleration. Well, this would be the change. A of t is going to be the change in your velocity. So that's acceleration. Think about the velocity. So you're traveling 70 miles per hour, you're on the cruise control, and you need to pass a car. You step on the gas pedal. That changes your velocity. So now your velocity has changed. Now you've increased your speed, right? You're traveling 70 miles per hour, step on the gas pedal, now you're doing 75. That change is called acceleration. And then there's also deceleration. Same idea. Negative acceleration means you're slowing down. You're changing your speed here. So let's just say you know that sometimes you're behind that semi and then that really fast car doing 90 is coming up from behind you, so you can't change the other lane, so you have to hit your brakes. That situation, you have now slowed down, still goes under acceleration. It's the change in your velocity. That's what's happened. That's acceleration. And this is also the second derivative of position. And that's the main idea. So let's look at these graphs. Pay careful attention. Look at this one. This is the graph of position. This is the graph of velocity. That's what's going to get you on the AP test. They both tell us a lot about the position, a lot about the velocity. We can learn a lot from both of these, but realize what graph we have. Velocity being representing the speed and direction. It represents the slope of position. And then you see these are velocity graphs. So for this one, they're giving us a position. This is the basic graph and idea of this. So this one is what you think would be happening. So an object's moving along a line. The following graph gives the object's position relative to the starting point over time. For each point on the graph, is the object moving forward, backwards, or neither? So if you look at this spot on the graph, what is going on? So are we moving forward, are we moving backward, or are we doing neither? Now remember velocity. If our velocity is positive, then we're moving forward. That means that x of t is increasing. Similarly, if it's negative, we're decreasing. So what's going on here? What's our position doing? Our position is decreasing here. So we're moving backwards. We're in San Diego here. Now we're coming back home, and then we just start heading to Yuma, right? That's what's going on. The x-axis would be right where Holtville's at, if you think of that previous example. So we have a negative velocity. We're moving backwards here. Right here, we'll talk about that in a little bit. So on this point, we're increasing. We're going up. So this, we're moving forward. We have a positive velocity because our position is increasing. You know, if x of t is increasing, that means our velocity is positive. So let's talk about these 2 points. We're turning around here. We're heading to Yuma, boom. Get mad at the kids, turn around, right? So right there, we're not moving at all. We have stopped. And same thing here. It stopped. And you could see on this graph, moving backward, stopped. Moving forward, stopped. By the way, if there was a point right here, this has a horizontal tangent, so the slope is 0, we would have stopped. That would be like a restroom break. You're heading back home, you stop to use the restroom, and then you continue to head back home. You continue to increase afterwards. That would be still a stop right there, but they're not asking us to describe that point. So let's look at what happens if we have the graph of velocity. You got to think about this a little bit differently. Same rules though. Velocity, if it's positive, then our position is increasing. So if you're going to think of this as the position graph, you'd be like, hey, we're stopped. But that's not what's going on here. Technically, velocity is at a maximum. This is actually the fastest we're going. This would be whenever velocity is positive. We're above the x-axis. When you're above the x-axis, it's this whole interval here, we're above the x-axis. So that means that our velocity is positive. So that means the position of the object is increasing, meaning we're moving forward. Similarly down here, because it's negative, not because the slope is negative, but because we're literally under the x-axis, or the time axis in this case, our velocity is negative. And if our velocity is negative, it's the inverse of this. It's going to be decreasing. So I don't think it's the inverse. I forgot the name of that term for that. But that's going to be decreasing or moving backward because our velocity is negative. Right here, our velocity is 0, so we have stopped. Remember, this is the graph of velocity. It's the graph of the rate here. It's not the graph of the position like we're looking at here. You know, decreasing, so it's going backward, increasing, so it's going forward, and then at the peaks, it stopped. Over here, it's velocity, it's the rate. Our rate is at a maximum, so we're moving forward here. Down here, our rate is negative, so we're moving backwards. Our rate is positive again, so we're moving forward again right here. And then at the x-axis, our rate is 0, so we have stopped. So right here, because it's velocity, we're moving backward, stopped, forward, forward. Okay, last one. They're going to be asking us about speeding up or slowing down. So remember what we said about speed? Speed is the absolute value of velocity. So think about that. How do you do an absolute value graph? So we want to know is speed increasing or decreasing. What you're going to do is you're going to look at the negative part of the graph and you're going to flip it. That's how you do an absolute value graph. If this, for example, this point here is like when x is 7 is basically negative 2.5, that output just becomes a positive 2.5. So basically that graph is just going to be the speed graph. This is velocity, so the absolute value of speed would be something like this. So speed, this is already positive, this is okay, but then we're going to take that negative portion and flip it up because speed equals, I'll just put it right here since I already wrote speed equals the absolute value of velocity. So we just take the negative values and we just want to make them positive, that's it. So the values are negative, let's make them positive. So when are we speeding up? When are we slowing down? So right here, our velocity is increasing. We're speeding up here. Velocity is increasing. So we're not really thinking about, obviously velocity is positive, so we're moving forward, but more particularly, this one's asking, is your speed changing? So yes, it is. It's speeding up. But right here, our speed is decreasing. It's on a downfall, right? The acceleration is actually negative. It's positive here and negative here. And then last, there's this point. Which would be right here. And so it is speeding up. If you were to look at the speed graph, our speed is actually increasing. It's a little bit backwards when it's upside down. But remember, we're ignoring this graph now. This is our new speed graph. So this point, it's actually speeding up. Velocity is decreasing. It's going down, but speed is increasing. So when you're underneath the x-axis, and we're going to take a look at this in the next assignment, it kind of flips what's going on for speed. Because you got to picture it when it's this way. So when our velocity is negative, meaning under the x-axis, when it's negative, you'll notice that if it's going down, once you flip it, it's actually going up. And then similarly, let's just say our graph, let's just say it did this. So we're going to reflect it back this way. And we're going to let's just focus on this point. So right here, when we're underneath the x-axis, once we flipped it for speed, even though its derivative of velocity is positive, even though slope of velocity is positive there, we're actually slowing down in regards to the speed function. So it does the opposite of what you would think. It would do the opposite when it's underneath the x-axis for velocity anyways. And that's going to come into play in this next assignment, and you'll see what I'm talking about. For this one, same idea. We're talking about speed on this one. Is it speeding up and slowing down? So speed, you just got to make sure you flip the graph. So you're going to be paying attention to those points on a flipped graph, and that's what's going to happen on that assignment.